All right, guys, so we're going to start talking about nuclear chemistry, which is the reactions that occur inside the nucleus of an unstable atom. In this unit, we're looking to, number one, define what are the types of nuclear radiation. Number two, be able to balance a nuclear equation. And number three, differentiate between fission and fusion reactions. So first, we need to remind ourselves about nuclear notation, which is what's going on right here, where we're either writing the mass number over the atomic number and the element symbol, or we are writing the element's symbol and the mass number so that we can identify what isotope it is that we're dealing with. So we've talked in the past about how elements can have different isotopes, meaning they are the same element with the same atomic number, but they have a different mass number. And what we may or may not have talked about in the past is that if the element is unstable, then it's called a radioisotope, meaning it will be radioactive and it will undergo decay in order to transmute into a more stable element. There's a couple of ways we can determine if the nucleus is going to be unstable. The first way is by looking at the nuclear binding energy. The higher the amount of binding energy that is in the nucleus, the more stable it is. We can also look at the proton to neutron ratio of the isotope. The further away that gets from 1 to 1, the more unstable the nuclide becomes. So here is an example of a band of stability graph. So here in the black is where we're having the stable proton to neutron ratio. And then as we move outside of that ratio, either way, we can kind of determine what kind of radiation the nuclide is likely to do in order to become stable. There are 3 types of radioactive decay that we are interested in for this unit. There's actually more than just these 3, but these are the 3 that we want to know about here. The first type is called alpha decay. Alpha decay is where the nucleus is going to emit an alpha particle, which is symbolized by 4/2 He, because this is a helium nucleus. Then beta decay, it's going to emit a beta particle, which is basically an electron. And then gamma radiation has no mass and no energy, but usually accompanies either alpha or beta decay. So in an alpha decay process, the mass number of the radioactive isotope will decrease by 4, and the atomic number will decrease by 2. So in this balanced nuclear equation, we can see that we started out with an isotope of polonium, polonium-210, and it's going to give off an alpha particle here, and what's left over is lead-206. Alpha decay likes to occur in very heavy nuclei, so you're looking at like anything above atomic number 82 likes to do alpha decay. But this is a very heavy and very slow form of radiation, which means it's not very penetrative. You will not absorb this. Your skin will block it. So you're probably exposed to alpha particles every day of your life, and you would never know it, especially if you have granite countertops in your home, because they are a source of alpha radiation. Beta decay, so we see here in this equation, what's happening is that one of the neutrons in the radioactive isotope is splitting, and the electron half is being emitted. So the mass number of the particle does not change, but the atomic number increases by 1. So this is an example of carbon-14 undergoing beta decay to form nitrogen. This is more common in the nuclei that have too many neutrons, so the neutron ratio is what's higher. Carbon-14 is present in all carbon-based life forms, including you. So again, beta decay is all around you, but this is also not very penetrative. It's a little bit faster than alpha decay, but it can be stopped by 1 inch of aluminum foil. Gamma emission, on the other hand, doesn't change the mass or atomic number of the particle, but it does decrease the energy of the atom. And if you remember our electromagnetic spectrum talk, gamma radiation was on the far right of that spectrum, which means it's very high energy. It's also very penetrative. This is the kind of radiation that you need to worry about because it takes like several inches of lead or steel reinforced concrete to absorb it and not let it get to you. So this one is why when you go to the dentist or you go to the doctor and you have to have an x-ray, they drop that lead apron on you because any radioactive particle that they're using to make the x-rays is also going to have some amount of gamma emission accompany it. Not enough to hurt you unless you like continuously get x-rays, but enough to be concerning, especially for like your gametes. Your sperm cells and egg cells are the most sensitive to this kind of radiation. So next time we will talk about balancing nuclear equations.